Okay, so listen, it's my pleasure to introduce Monica Olvera de la Cruz, colloquially known as Monica. If you just say Monica in the soft matter community, everybody knows who you mean. So she started off life at a very young age, as they say, um, working in, she did her graduate work at Cambridge, working in the group of Sir Sam Edwards, who produced such other luminaries as Robin Ball and Mike Cates, and someone named Jasna Bruich. But back in the early 80s, Monica was there and she did her graduate work with him. She ended up in I forget the exact trajectory, but very soon thereafter, she ended up at Northwestern University, where she has been for essentially all her career. She's known for her work, particularly on polyelectrolytes, but she's worked on a wide variety of soft matter systems, on membranes, on colloids, on all sorts of different things. And so we're very lucky to have her here today, and we're looking forward to hearing her talk. So welcome, Monica.
And maybe thank you very much, Dave. I'm going to talk about diving soft materials with magnetic field, and is the work of my students, Chase, Han, and Abed, and in the past, Joshua and Pablo. Joshua left already in the province of Juan Pablo in Yucatan. The experiments are in the lab of Sam Steve. So I don't have to make, oops, interesting. I don't have to make a long introduction about magnetic colloids because, you know, everybody's familiar with them and they have been used in many applications. And generally, you know, they are now very interested for their active matter influence, you know, to organize. So these are some examples of work of others, including a review article of Michelle Biscoff, which worked in NYU with pole shaping in these magnetic colloids. What I'm interested in is introduce elasticity and deformation in with magnetic particles. And so I have been doing a lot of things on hydrogels where you have composite materials and you add another type of fiber and the hydrogel contracts and so on in different situations with temperature, for example, changing the hydrophobicity of the material. And also in buckling of things that have mechanical heterogeneous properties. Like, for example, you take a rubber band, stretch it and glue it to another one that is not so stretched. And when you buckle those structures, they form sort of these, what I call perversions, or people call perversion, which is change chiralities and so on, and shapes that resemble living matter. And also buckling of shells. And I'm going to try to tell you how in the buckle of heterogeneous, mechanical heterogeneous shells, I have two components, what happens when you add magnetic, supermagnetic particles, or in a hydrogel, ferromagnetic particles, and you actuate them, okay? So with that, you know, I'm gonna start just giving you the examples. And some of them are unpublished work, but the first one is magnetoelastic filaments and membrane actuators, which has been published. But then I'm going to try to use what we learned there to do magnetoelastic swimmers. And at the end, I'm going to talk about the light activated magnetoelastic walkers. I deleted one topic. Anyway, so there are two types of magnetic systems. There are ferromagnetic systems that have a permanent magnetization, and I will describe those at the end. They sort of have hysteresis generally. You go very strong fields, external fields, you know, but if you stay within the linear regime of magnetization, external fields, you can actually actuate very interesting matter. I first will discuss the superparamagnetic case, where you don't have a magnetization system, but you know, when you apply a magnetic field, there is a susceptibility, you know, response of the material, which becomes develops a magnetic moment that is proportional to that external field and the susceptibility parameter of the system. And so in that case, you know, you can actually assemble a structure that are superparamagnetic particles in different situations. For example, this is the case where you have an external magnetic field H in the direction z-axis. And so the particles develop this magnetic moment mu, and they organize parallel, they form bands parallel. But if you actually have start precessing the field, here is a rotating, okay, by generating the axis field, then you can actually assemble these structures instead of in lines, in planes. And so these are just cuts of planes, and from the top, you can see that you start forming membranes, two-dimensional membranes. So this is what we're going to explore here, and but not let them free, but making filaments of it. So you can glue them, like say, with a polymer. And so there have been some work, that you can actuate it. For example, here is this filament is pushing some matter, and here is swimming up. This is the case of a lazy thermal that, the filament is directing it. So, there are some various examples of superparamagnetic filaments. And the work, started to be characterized by a group of Alice Gast and others who have done a lot of work on it. But here's an example where you can see that you put these filaments, and now, initially you have the field in this, say, direction Y here, and then you switch the field and you can change the conformations. And in particular, you can actually now, characterize them and discuss the properties. For example, the extension, the Young modulus they can have, or in compression, or bending rigidities of these filaments. Depending on how you prepare them, of course, you can change these properties. These big particles here are the ones that exert in the force on this filament to measure the properties. So let me just look at how we sort of model these numerically, and then I'll show you how you can make sometimes some theory. You have Hamiltonian that has the magnetic part and the bending part, and then you put also hard cores because the particles cannot overlap, and rigid bonds if they don't they are a little bit not extendable, and you put Langevin dynamics, and you can calculate these numerically by just calculating the dot product of this unitary magnetic moment that instantaneously develops when you put a field H. But now, instead of rotating it, you're going to precess it at an angle theta that is not pi over 2. So you can represent that instantaneous, magnetization that you cause in the particles by just this frequency cosine of theta sine theta in X and Y and Z. And so what do we do with this? And this will be the bending rigidity of the filament, and the energy you have to pay to bend it, and with respect to sort of a flat case. So when you do this numerically, you can work in different regimes. And in a regime where you apply very fast, the precessing is very fast, you can actually average over a period this Hamiltonian. If you only assume nearest neighbors, you can get very nice expression. If you make the average, you have two terms. This is the alpha, this is the filaments, and I'm going to represent it here like a line, and I put it in purple so that you know that these are these bits, purple bits, but it's just an inextensible just line that is bended. There is the phi angle with the neighbors R, of all where the particles are, and then this is the theta angle where you are around where you are precessing the field. But since you average the frequency now, it just depends on these parameters. And if you make an approximation that you only take the nearest neighbors in the magnetic density, you can write the whole Hamiltonian as the sum of just two terms, the bending and the magnetic part. And so in a fast precessing case, so when you write that, you get, if this is the curve, the t is the tangent, this is the cosine of alpha term minus 1/3 is multiplied by an m of theta that change sign depending on the theta, right? So the m of theta goes like mu squared, this is the different length, this is just particular length over the distance between these particles. And the theta, critical theta is 54.7 degrees, where this becomes 0. And if you have a precessing of the magnetic field that is less than this critical angle, then you have the m of theta positive, and if you have it greater, then m of theta is negative. So you have this condition, and remember that we're doing nearest neighbors, but people have shown that it's pretty good to describe, and we saw it numerically because when we do some analytic solutions with this Hamiltonian that is simple, you get actually pretty good results. You can only make these solutions in particular case. The other term that is missing, that is not described there, is the bending, that you can also describe, in terms of the curvature, 1 over the radius of where you're curving this sort of curve, then these beads are now connected in this line. So what would you get if you have these filaments free is that if you have the field precessing around, well, not precessing, just in the h-axis, if positive, you get the filaments aligning, like if they were just the two particles. If you have the theta angle, then they're random, they are random, these filaments. And if you go and precess at an angle that is pi over 2, then you get this flat case that I told you in the beginning for the simple particle. So you recover the same things. But then when you apply the force, and these big particles here are the force, and here are the force, then these filament buckles, right? And it buckles only into 2 types of curves. If you are precessing the field at the theta larger than the 54 critical angle, then they form a helix. You can see how they form the helix, and it's out of the plane. And if you have a theta angle less than the critical angle theta, then they buckle into sort of this shape, like that. So this on the plane. So they buckle on the plane or off plane. And so this is if you are holding it in the same direction, which I call vertical, of where the field is. So of course there is a symmetry because the Hamiltonian depends on the square, of this mu that is proportional to h. And we define the magnetoelastic parameter as not of m of theta, but said m prime, which is just the precoefficient, just to get some value, and then the magnetoelastic parameter is this m prime, the precoefficient, over the bending rigidity and the length of the filament square. So this is a dimensionless parameter, and you can vary from 10 to the minus 3 to 10 to the 4 in sort of the typical examples that people have manufactured, done, or synthesized. Okay, so now let me go on and talk about the what happened. I mean, why did this take this form, and how can we predict it? And indeed, you can actually write the Euler-Lagrange equations of these systems. And when this is the vertical fixing, and you put the force, you can calculate the shapes. There are complicated equations, but you can calculate, assuming certain symmetry, around this axis. What happens if you change this length, or L0, or some length L, ST, over the length of the whole filament? And depending on the gamma magnetoelastic parameter that I just defined to you, you get different curves. So it depends on how much you contract, and what is the gamma value. And you get different shapes. This shape doesn't really arise. This is just mathematically from the solution, assuming symmetry around this axis. But the reality is that it's more complex equation if you don't assume that symmetry. But you can show that at a critical gamma and contraction, they actually flip to one side. So instead of developing 2 bulges, they just flip like that. And this is where we get numerical. So, sure.
有多少都给鼓励。那个听说是那个副导。
I need to mute everyone.
Is somebody asking a question?
I was going to ask whether you put viscosity in.
The viscosity here is precessing so fast that you don't have time to have a Brownian motion. I will tell you what happens when you do have a slow precession, because it's instantaneously. So it's much faster than any heat back that is possible. So it's just like a steady state shape. When you have a low precessing, then of course, the angle changes, and you have a frictional force opposing it. And then you get torques and you can rubber it. This is just frozen in, and you apply the fields very fast. You know, you have a steady state solution for the shape.
But the magnetization can't follow the field if it's very viscous.
They are superparamagnetic particles. So
Uh-huh.
the particles
Yes, fine.
instantaneously, yeah. The ferromagnetic ones, you're right, it's completely different story. These are
The
superparamagnetic.
spin orbit coupling is low.
Yeah. So they're just
Yeah.
instantaneously, and when you take them on instantaneously, it goes away. Okay. Or relax. I mean, they have a susceptibility, but it's very fast. So this is the fast processing case. It's a very good question. I'm going to discuss the other one later. I wanted to note that before I used to have this in black, but Paula told me that it's not clear where were they. So now it's purple. It's the same beats in a continuum. Anyway, so long time ago you asked me that, Paul. What was this little line? So this is the other case when the theta is larger than the critical angle.
Monica, you need to unmute yourself. For some reason, you went into mute mode.
Oh my goodness. So everything I said, you didn't hear, but you saw it. I mean, I'm talking about the two cases in the direction, you know, of precession. Okay, so I'm sorry about that. So this is the case where in this situation where you put the force, it forms off the plane because you are above the critical angle. So, so something to note that is going to become important in the rest of the talk is that in these cases, you know, the actual shapes depend on whether you fix the ends in the horizontal and you are processing the field in a direction in a direction vertical like that, theta, or if you fix them in the vertical. And so in this case, you can see that the curves, the minimum is this. This is not the minimum for the case theta greater than n, but the helical, but you will get other shapes that are very different than if you fix it this way. So this will be the gamma negative being minimum in this configuration horizontal. So just so you know that it depends on how you orient or fix your filament. Now, if this is a question that Paul was asking, what happened with the friction? And I didn't write the questions here, but indeed, if you have the B of theta that is developing, changing with the frequency, and it's a slow frequency, you are developing a phi angle that is changing. And so that develops a force, instantaneous magnetic force that depends on sine W theta and the mu zero square plus this delta phi. And that generates actually a frictional force that is opposing that magnetic force. And so the equations have this magnetic force plus, you know, the frictional force multiplied by an angle that changes with time. And so it becomes, you know, you can solve it numerically. And what happened is that then you have a torque that curls the ends in the limit of very slow frequency. And so that will generate, you know, curls the top because you have the forces of instantaneous magnetization in a certain direction, cursing in the opposite direction, top and bottom, and forms this shape, which my student hand tell me that somebody actually see them experimentally now, these curl shapes. So you can make some limits on the theory of how much will curl and so on, but only in very, very slow processing is a very complicated problem now. But in summary, you can have these individual filaments that can make to exert controllable tensile forces along the precessing axis that can be attracted or repulses, and these forces are you know, can be exploited for actuation. And in bulk, the filaments can be rapidly assembled into different configurations, depending on how you choose the parameters of the field that you put and the angles, and you know, you can have more complicated than just constant precessing fields case. But I'm not going to talk about those. Now we're doing exactly the same, but it's not a filament, it's a membrane. So it's adding up a little bit more of complications. And so this is the same case that you vertically do that. And so it wants to buckle. And if the precession is larger than the critical angle, it would buckle in different shapes. So you can do that. For example, this is assembled membranes in the presence of the field, external field parallel. This was done with a group of Chad Merkin, but you can also, and this has not been done, if you precess them, you can assemble them in flat membranes too, and then so polymerize them and make these sort of flat membranes. So let me just go like, now we do exactly the same as I told you before, and I'm not going to talk about analytic solution or other numerical solutions, but just the simulations. And you have the same terms, the dipole, the bending, and the stretching of the material, and so hard cores. And if you have just Langevin heat bath, you can put it depending on how fast you precess, it was going to be important or not, as in the other case. So let's just talk about here the fast precessing case. And the gamma, now I'm going to absorb in the M prime the theta. So the gamma can be positive or negative. And remember that you are contracting during the length L0 over certain length Z in the material. So I'm sorry for the change. This was Z before, but now it's like this compression of the membrane, and this is the initial length of the membrane. So if you plot it, you can have regimes of where you can buckle the same way as the line, or flip it up if this is very negative. I told you before, it flips. The filament, also the membrane flips. But if you move the theta angle from negative to positive, because now is the horizontal configuration, so you are compressing it this way and the field is in this direction, you can generate other types of buckling. Another way of actuating it will be to switch the angles, twisting it. So the reason why I'm showing all this is because I think one can really take advantage of all of this actuation to make a lot of possible shapes and motion, and also, later on you'll see you can actually make them swim, but this is just the steady state case. So these are the horizontal ones, and in this region when it's positive, you have just the normal, you remember these shapes that I told you that develop that are very different than the shapes when it buckles roundish like that. So if you have a critical amount of this gamma, which is not the magnetoelastic parameter, but having the theta on it, you can get, the bucklings into more sort of drastic shapes here that develop these bulges and so on, as opposed to just like normal shapes that are simple shapes, are these round or the flopping ones. And you can calculate the energies, when you, because have this deformation. Hi. So with that, you can see when you change modes of having, your buckle shape more complicated, when, wants to be more flat and is fighting all of the elastic force and the magnetic force on the conductivity. And as well, when you, instead of just moving the L, you change the angle, the twisting angle, you can actually generate hysteresis, meaning that, when you start increasing the magnetic field and start twisting at different gammas, you can buckle in shapes, but when you come back and release, you actually generate different shapes. So it has some hysteresis on the structures here. And so this is the whole map on the twisting angle. Instead of L over L0, now you change the 2 phi angle of twisting. And again, if you are in a gamma precessing negative for this horizontal one, you get these shapes that are very different if you go to the positive gamma, which is below the critical angle and above the critical angle for this case. And you can see sort of like these very complicated shapes to the better. And the hysteresis in the energy when you cause the deformation and when you return. So all of these, all of these can be used now to study more another type of buckling. This is also a constrained membrane, but it's constrained on a spherical morphology. So this is the same superparamagnetic crystalline structure. And people know how to treat the buckling of these structures just from elasticity. And just the whole Hamiltonian in this case will have two parts. One that is the elastic part and the bending. This is the elastic of the structure, closed shell, and this is the bending, and I'll show you how numerically one implement. And then you can add the magnetic force the same way as we are in the membrane. And so now, now we'll have two parameters. One will be the magnetoelastic parameter that I described before in terms of this M that is the response of the system to the field. And the size is now R squared of the bending. And then the Van Karman parameter that determines when a structure that is closed buckles into an icosahedron. And that depends on the Young modulus, also the size and the bending rigidity. So this is work by Han, my student Han. And so we were calculating now, the buckling. So here's just a sphere. When you start, you add the terms and you can implement the stretching and the bending, making the structure of triangles and calculate, how much when you actuate this structure, how much you stretch it, or if it's, if the structure has no magnetic field, you still can actually calculate when you deform this structure, how much elasticity changes, or the bending by calculating the angle between the two vectors when you change the curvature. And that is well known, and it produces this sort of buckling. Is associated with like a defect because these structures, to be crystalline, they have to have pentamers, and the pentamers produce a strain and energy that is repulsive between them. So you can have these pentamers. In order to close in a sphere, you have 12 of them, and the 12 pentamers are further away from each other because they cause a lot of elasticity in the system that can only be relaxed by buckling, into a cone, these defects. So when you have the closed structure, just by sort of like well-known, theorems of closed shells, you have to have these 12 defects in this structure and they buckle simultaneously, and that's how you get into the icosahedron. So now when you add the magnetic part, so here you have to have the extra term in the free energy. So you have two terms, the elastic and magnetic. So here is the magnetoelastic parameter increasing, and here the Van Karman parameter increasing. So this is the Young modulus increases over kappa, and this is the M magnetoelastic parameter, which is M characteristic mu square over the bending increasing. So if you have no magnetization, you get this icosahedral buckling when you increase this Van Karman number. But if you start having increase in this parameter, you get buckling to very different shapes, including these sort of like complicated shapes that have nothing to do with the initial, icosahedron. So this has been published already. And what Han is doing now is trying to explore the fast precessing of these structures. And now you introduce the M of theta parameter, and you can have, if you are below the buckling, you can actually generate these shapes, lattice. And if you're above the buckling, it's much more complicated shapes. Okay. So that just explains this simple structure. But we want to make them swim. These ones will not swim. They're homogeneous. And we want to know how to make them swim. So let's just start with, remember the square one that was buckling by supporting it. Now, if you let it free, you can oscillate and have amplitudes along the z-axis of the membrane. You can develop amplitude depending on the orientation you have with the field. So this is what we are starting to explore. And this is work by Chase. First of all, in order to make these nanostructures, because these nanoparticles, can be 20 nanometers to 50 nanometers, and you're making these membranes with just 100,000 of them. So they actually don't have inertia. So you have to be able to work in low Reynolds numbers to make them swim. And in this case, the friction is dominated as opposed to the inertia. And this is a theorem that in order to make it swim, you have to make a non-reciprocal cyclic oscillation, right, on these materials. So this is what we're trying to explore, how to make these low Reynolds numbers with these membranes of superparamagnetic particles swim. So the first example will be to consider back again the flat case and just to see the forces, and but let it free instead of compress, constrain in the sides. So if you let it free, you can develop, some wiggling on the surface of this structure now. And so you have an amplitude, that develops, and this amplitude is propagates radially and on the surface, right? So it's just sort of like the deformation that occurs, and that depends on the frequency of the precessing field and the angle of precession again, when you are above or below the critical angle. And so you have different types of modes. Some of them are just wobbling, some of them rotate, and some of them, my student called these dancers. So the phase diagram as a function of the frequency of the precessing field, the angle of the precessing field for the membranes in this orientation. He makes the phase diagram. So here are the dancers, and here are just the traveling waves developing along the membrane for different values, the small values or very large. And then these, the dancers are here, they bubble around. This is what you can do with an sphere, and this is just the ones that rotate like that. So you can actually calculate how this amplitude B depends over R, the radius, on this sort of like inverse frequency, and it's linear with some pre-coefficient of depends on the theta and the parameters and the viscosity and so on of the system. So once you characterize these, you can try to sort of see whether you can generate swimming, and you have to make the motion non-reciprocal. So for that, you really have to cut or make some asymmetry in your magnetoelastic membrane. So this is the magnetoelastic membrane seen from the side, and this is the z-axis. And so you can follow the flows that develop when you are actuating it, and when these sort of like amplitudes are developing in the structure. And at the end, calculate whether it swims and what is the velocity of the swimming for the one truncated versus the one that is non-truncated. And the goal is to try to understand, how to make it swim, why, and what shape. How does it depend on the cut, degree of asymmetry you put on the membrane. So again, you have the field in this direction, and here is the membrane this oriented this way. Okay, this is the H. Precessing. So when you analyze the fields at different positions with respect to where the membrane is, you can see that when an amplitude develops, you are actually generating some flows that are circular here, and this direction moving this way in these amplitudes. If you truncate it, and let's call the truncation as the ratio of H that you cut over 2R, you can actually see that you have a finite velocity developing. So these members start doing motion, circular motion like that. Okay, so they do have, and the velocity is linear with S to the 3 half at this point and 1 over the frequency. And so we're trying to characterize that. As I said, we still are just trying to write up this. So the summary of this part is like, you precessing magnetic fields induce traveling waves in these membranes, and these traveling waves produce this short-range circular flow perpendicular to the membrane plane, and that can be explored or explored for swimming. So the other models is like, if you want to reproduce some of the biological swimming cases, this is a very interesting one, and I'm sorry I forgot to put the reference here, but it's in the web. And so these objects flow, swim not because of the tail, but they are deforming inside the matter. And so there are, I already told you the traveling waves and the helixes. And so in order to make these membranes that I told you, we need to do now 2 things is like constrain it. So that they have different mechanical properties. So this is if you put the field in one direction, increase it and then decrease it, you can see that this magnetic part, contracts, and you can actually generate these sort of like complicated bucklings depending how you choose the field. So I'm going to show you an example of how you can get this. This is an experiment, you know, that sort of represents how you can make something move if you have a non-reciprocal deformation. So when you make the membrane having two mechanical properties, one more rigid than the other one, basically you are constraining the part that you are deforming, and you can actually deform it and actually make it swim. This is the final velocity of this closed shell. So it's deforming, here is contracting and expanding, but at different rates. And so this is just, again, how you select the fields in the X, Y, and Z direction. So it's the axial, is the zero in one axis. So this is just how we sort of are exploiting and exploring all of the things we know on elasticity and the filaments, paramagnetic filaments, to make more complicated systems and optimizing swimming. This is at low frequencies more complicated. And so you can see the membrane, you know, is rotating and developing and buckling. And this is, you know, the previous one was fast precessing, and this is slow. So I'm just going to complete this part of the magnetoelastic materials that are using superparamagnetic particles competing with elasticity to make these, you know, artificial swimmers. And I hope I have persuaded you that you can do them. And you know, you have to synthesize them, but still, you know, we can design a lot of possible swimmers and different actuation mechanisms for them. So I have the last example that I told you I was going to cover 3 examples, which is the ferromagnetic hydrogels. So people have explored in elastomers how to put ferromagnetic particles at different positions. And then because you fix them with elasticity of the material, you can actually actuate and deform them. We are going to make this in a material that is can swell with water, so it can change its shape by swelling, and I'll show you how it's done. This is a recent paper with Samstu that just got published, and this is what we call this hydrogel robot. This is made of ferromagnetic fibers in a hydrogel that, when you expose to light, contracts, and then here the precessing field is really rotating field around θ/2, and if you change the direction, it can walk up and down, you know, a tank. It's very small. It's 3 nanometers, this length here. 2 millimeters, sorry, not nanometers. Okay, so this robot can actually be actuated to pick up things when you put the light, and it curls with the light, and it can actually roll and also open up and deliver the object it takes, walk with it. I mean, it can do a lot of things, okay? And so this has 2 modes of operation. It's light and magnetic fields. So, so the way it's done, this hydrogel, is you just have these fibers that are like 100 nanometer micron fibers that are ferromagnetic nickel fibers. And so initially just have the monomers, and they have a chloroform, a material that is going to be becoming hydrophilic or hydrophobic depending on the light you put. And when you put the magnetic field, you align the fibers, and then you polymerize this system with this spiropyran in. And this spiropyran is hydrophilic if it's charged and on in the dark, and if you put the light on, it becomes hydrophobic. Okay, so it shrinks. So if the polymer has certain fraction of this group, then you can calculate that when you shed light, you are going to have a reaction on the excitation, you know, where you will produce certain number of these hydrophobic groups. And that, of course, will depend on the intensity of the light you put. And you can relate, you know, this intensity, you have a decay of them and absorption in a material of certain thickness. You can actually absorb, you know, certain amount of this is the light. You can absorb certain fraction of them get excited, hydrophobic, and they also change the amount of light because they're absorbing it and releasing it. So you can calculate those systems. And now the free energy of the gel has two parts, an elastic part and the entropy of mixing due to the water. And so the elastic part, you just measure in terms of the deformation parameters lambda, which is the changes in dimensions in the X, Y, and Z, over the initial dimensions, very simple Flory-Higgins models, Flory models for the stretching. And you can actually also put the Flory-Higgins model that has only the entropy of the water, because the gel is only one molecule, and the degree of incompatibility of the monomers with the solvent. And so you can add to this the photoelastic part, and that just modifies this kite really by calculating how many of them are excited. So when you do this, you can actually very, very nicely predict what is the shape of your of the robot, or hydrogel. So this is the hydrogel, with the aligned the ferromagnetic fibers in this direction after you put the light, and this is what the theory will give you. So depending on the intensity, like if you have, this is just the steady state shapes they will take depending on the amount of intensity. So if the intensity is little, nothing happens. If it's too much, then all of it goes and becomes homogeneous again, because it becomes all hydrophobic, so it doesn't have gradients. So you need to generate particular gradients in the concentration of the water to bend it, okay? So you can calculate that. And now why does it work? Because the fibers, are oriented in this direction. So if you put a magnetic external field and these fibers, want to align to the field, so you're going to open up that shape that you generate with the light. And then if you reverse the field, now it's in the opposite direction, you want to compress it, okay? So these sort of mechanisms are the ones that produce actuation for walking. So in order to see how it works, you have to calculate the torques, that develop. And this, the color is the torque. This is the average magnetization in purple. And the blue is the rotation or precession of the field around this axis coming out, okay? The arms of this robot is just for stability, so it doesn't fall to the right or left. They are not really accelerating or not the motion. The other thing is you have to put here is the boundary conditions. Like if it was free, it just does this, but it doesn't work. You have to put the not slip contact, and so that it can actually walk in the surface. So all the time we are actuating this with an external field H, so that the total field from the magnetization of the fibers is within the linear regime. It's like around 160 Gauss omega minute Tesla. So it's a weak field. And the speed of these films that I show you is actually the real speed. It takes time to dissolve the water, but once you start actuating it, they walk at the speed that we walk, okay? So they are very fast. And so some of the things you can do is just make different modes. For example, calculate the torques. This is the experiments and this is the simulation with the torques that develop in a system that you need to control by the field to make it not only walk, but also turn, steer, and so on. So I'm going to show you, and with this film that shows how, this is my students predicting the fields to make a path at certain speed, and then you program the magnetic field in the lab of some Stube, and this is the actual robot executing the sort of set of instructions given, in the computer really, to calculate how to actuate this mini robot. So this is all I have to show you today. As I said, we're very excited, and some things have not been published. And I just gonna thank you for your attention and also thank my group who did the work, and especially Han, Avec, and Chase, which I don't recognize it here actually. Anyway, sorry about that. Okay, Han is here. And Chase here.
Okay, so we're ready for questions.
Hello.
Should I stop sharing? So I
Um,
can see you.
It's up to you.
It's nice to see you here. Okay.
So in those closed swimmers, I don't know what you want to call them, the ones that were made up of little spheres that undulated. How does that depend on the size of the spheres? There wasn't any scale there that I could find, and it must depend on
Right.
what the size of these spheres are.
The size of the spheres are generally determined by this delta L in the M, the distance between them, that closest approach if you want, maximum. So they can be, this depends on the R, how many you put in the big particles, 1,000 or whatever for the big shell, but the nanoparticles,
They're nanoparticles.
the nanoparticles is what determines really how fast or whatever you can swim. It's basically, yes, it's basically the magnitude of that M parameter that you can control. That is just mu square that has external field over delta L square. And so those are, yeah, I can actually show some examples of the values. But anyway, so it's the nanoparticle that controls very much how much you can, actuate it.
But how does the swim? How does it change if you make the particles bigger? Does it become?
You pay this. You change this precoefficient. The dependence on the size is just through the final R squared. Is like M R squared. That just tells you the magnitude you need for moving a large or small one. But to actually actuate them, you need to be within the nanoscale, low Reynolds number, in order to be viewed to this friction
But
force.
even micro.
They're just, you have the inertia. So I'm sorry, I don't know if I understood your question. How does everything depends on everything, I guess. But we are targeting a small particle. So you are within low Reynolds numbers. And that is determined by the size of the nanoparticle, not of the whole shell.
Right. But even micron-sized particles and 10 nanometer particles are both low Reynolds numbers. And I just wondered how it depended on your choice over that range.
Right. No, over that range, the actual, it is true, and some of the experiments that have been done are, varying between micron to nanometers, 200 nanometers, and the one we chatted were like 50 nanometers diameter. So it varies a lot. And they are all, still with low numbers. The parameters, we haven't done it or with someone to tell us exactly these values. I'm trying to get somebody to do these nanoparticles halfway, to put the paramagnetic particles in a closed shell. But yeah, so yeah, it's all a dimensional here. You notice?
Yes.
There are two gammas, and they depend on R and M and the kappa, bending rigidities. So it depends on how you choose the bending rigidities. The key things is like if you in order to make it swim, you have to have a rigid one and a softer one. And so for bending rigidity, so this one sort of holds these shapes and contracts it. And so, it's just playing with those ratios that matter. Yeah, and what you are exploring really is the relaxation of the elasticity to the deformation due to the magnetic field.
Other questions?
Hello.
Hi.
Hi, do you hear me, Monica?
Yes, how are you?
Actually, thank you very much. First of all, my name is Nadir, and I'm attending this seminar from Montreal, Canada. Actually, I have two questions, and I'm not sure if there is a time allow me to ask both of them. The first question, I want to know something about the method, techniques, instruments that you have used to generate and apply the magnetic field precisely and control the magnetic field as well.
Yes, these the magnetic field. The magnet was bought by Samstub, and it actually goes to only 1 Tesla. You don't need a very large one. And this is for the robots with ferromagnetic particles. And it is controlled, in fact, Abek and Han, my students, can control it, from the office or the theoretical office, but also you control in the lab. And so I am not familiar with exactly, I don't know the brand or this. I just know that it can have different direction X, Y, and Z for the magnetic fields, and you can control it independently. And it's up to like 1 Tesla. And the frequencies are not also, the ones that you would like in the high magnetic field lab. I mean, they're just, I just showed some values of frequency in my plot. But anyway, I don't know if Han is here and can tell more of it. Listening, they actually are the ones that manipulated from their office the values. And the other question was what? I mean, the techniques. The techniques I show are just numerical simulations. And when it was possible to do some theory, the analytic work, the initial part was done by a mathematician, Pablo. And Han has done a lot of the theory on the closed shells buckling. And this using, different numerical methods. If you're going to put hydrodynamics, you can go with some methods that are lattice Boltzmann, and Han has used some other ones that is sort of equivalent to visible particle dynamics, but point particles that have viscosities and so on. So it's kind of a little bit average. So it depends, which part of the systems that you want to know. But yeah, I'll be happy to talk more later.
Yeah. So in general, Monica, you can apply the magnetic field in a very specific region or area and control that magnetic field magnitude and direction. Your instrument is able to do so? No,
this field is total. What you can control and later is the light, from where you shed the light and so on. But not the magnetic field. You can only control X, Y, and Z, the frequencies and magnitudes, to generate those things. But it's not local.
Okay. Do you have time to ask the second question?
I ask my host.
Sure, go ahead.
Okay, thank you very much. I want to know something about tracking these objects. Like when you apply the magnetic field and your nanorobot moves or your membrane moves somewhere, do you have any idea how to do the tracking for the next movement of this object?
Tracking, you mean in the lab? I mean,
tracking the object. You apply the magnetic field. You are assuming that the object moves 1, 2, 3, 4 nanometers in this direction. We need to know is this trackable so I can know it's really went to that place?
Yeah, that's exactly the whole point of the last part. We design a path for that particular robot. It has to do with how much light you put, and then the fields. You have to calculate the torques to make it steer or walk at a particular speed. So that's what I was showing in the last film. You can actually program the magnetic field to have a specific path.
Yeah, this is your designed or a planned or your desired path.
No, but the second one, there were 2 films. One was the theory, and then one was experiment.
Okay, but it's measurable. You can measure where it goes.
Yeah, of course.
How do you measure where is the object?
It's in nanometer size, millimeters. So they're millimeter size, so you can see.
Okay.
Yeah.
Okay.
They are not nano. The robots at the end are actually large. And,
okay.
They are macroscopic. Yeah.
So you track it by camera? Or
you can just see it with AI, but I guess they track it like that. I didn't ask them exactly how they measure that, but we just design it and they program. My group actually programmed that magnet to do that.
Okay. Thank you very much. It was in general very informative seminar. Thanks a lot.
Thank you.
Can I ask something?
Oh yes, sure.
Monica, first of all, thank you for seminar and good to see you. And second of all, first of all, it was of course not a question, but second one will be a question. So consider your swimmer, this flat sink which fluctuates and swims. What happens if I now process magnetic field in the opposite direction? Like it was like this, and now I go like this. Does it swim in the opposite direction, or what happens?
This is an excellent question. The swimmer, in actually to swim in a straight line, these swimmers with this precession like that only do circular things like this. If you wanted to go straight, you have to do what you ask. You have to go and then change, stop, twist it around and move it again. So you have to develop a sequence of magnetic fields that will actually make it go straight. Right now it's just going circular.
And if I flip the direction of precession, then it follows the same circle in opposite direction.
Yes,
right?
you only do that, so it won't go straight. If you want to go straight, you have to play more. But yes, it just goes the opposite.
I understand. Okay, thank you.
Monica, when you make the membranes, are the particles, are the magnetic particles self-organized, or you put them down as you like?
These membranes, both of them are crystalline in a mesh, okay? And that's why they buckle so nicely and beautifully. So you're the only one who's going to make them so crystalline and beautiful, aren't you? And then, I mean, of course, you have to have the crystalline like that. So that's the way we started the closed one. And so the other one is in the triangular thing. It just, you know, in principle, you know, you can't make them also not perfectly, and because it's just discretizing an elastic model or whatever. But the ones we do in the numerical simulations, they are crystalline.
So, okay, but so you in both the membranes themselves and in the closed structures, you could put the particles anywhere you want, right?
Yes. Yes.
So you could, for instance, on the sphere, make a square lattice, which would give you a different buckling. Or in the planes,
cube or whatever. Yes.
In the planes, you could put more on one side than the other.
Right.
Right.
Yes.
So you have another degree of freedom to play with, which is where the magnetic particles are.
No, that's a very good point. In fact, we're doing the continuum of the big ones with light, and you can make them heterogeneous, and you can actually make them in the lab very easily heterogeneous on different, you know, elasticity or bending, and then with different amounts of chloroforms. And so you can make what we call an active origami, right? And it develops the shapes and can change. And this is what we're doing too, but I didn't present here. So yes, you can do them like that. I thought you asked me how we're doing it, and they are crystalline, these ones. But of course, you can actually do other meshes and so on. In fact, you know, when we did the one on PNAS paper with Chase and Pablo, we did some examples on continuum grids that were actually squares and so on, and the bucklings were the same. Yeah.
Very cool. Thank you.
We have some other questions.
I'm going to ask a question that's a little bit self-serving, like I always do, which is, if the particles were made of droplets, and if they didn't have friction, and if they thermally agitated so that they wouldn't allow to move from the 2D construct that you make out of plane or what have you, would it be a fun game to play with your system to try to design specific interactions between regions of your membrane space so that they could do their origami?
Yeah, let me see if I understood you, because sometime it got, you want to put the particles in the interface of some droplet, say oil and water, and then you deform it. Is that what you're asking? As opposed to, yeah, with elasticity. But I mean, I guess you could do something, but the point here is that to make them swim, you have to keep certain shape. You're using the relaxation of elasticity to
Yeah.
make in the low Reynolds numbers to make this.
I understand. So that
I don't know. I mean,
need in the shape that you demonstrated nicely, the kind of minimal ingredients you need to get locomotion.
right, in the walking, if you put the particle aesthetically there and they are not elastically sort of trapped by the gel, it doesn't move, even with the ferromagnetic particles. Yeah, they just move, but they don't move the whole robot. You need to link it to the elasticity.
Okay. Okay. And then the fight would be between the interactions between the particles and the elasticity of the membrane that they're on. Okay.
Yeah, I wonder if by other means it can be the formed droplet with the particles, but anyway, yeah.
Okay, well, if there are no more questions, why don't we thank Monica again. And if you want to stick around and chat a little bit, we can do that more.
They told me to hang around here if anyone wants to talk to me after my seminar for an hour, so I'll be here. I'm very obedient, isn't it? Anyway, thank you very much for the invitation, actually. I was very happy to see you all, after such a long time. So hopefully next time we're in person.
Right.